So my talk is going to be on the modular simulation. What in the world is that? So a lot of folks in Silicon Valley believe we live in a simulation. In other words, a matrix. So Elon Musk, okay, this is what he says. There's a 1 in a billion chance this is reality. 1 in a billion, okay. Sam Altman from Y Combinator, they're the guys who invested in Airbnb and Dropbox. Both Sam and Elon have worked as scientists to help break us out. There's another smart guy. His name is Professor Nick Bostrom from Oxford University. He wrote, "Are you living in a computer simulation?" Why would such successful and smart people think such a silly idea, right? We're in a video game. Why would they think that? One reason, Pong. So this is November 1972. Okay, it's obviously not a very good video game, but that's what we had back then. In about 40 years, this is Cry Primal March 2016. It just came out. The game is set in 10,000 BC. This is actual game footage. It's not just like a artwork for it. So when you're playing around, look at the drastic change in it. But it's not just video games that we play. Look at the devices that we use. Oculus Rift. It looks very impressive today, but so did Pong in 1972, right? Who knows what could happen in 40 years? And this is just virtual reality. There's several of these realities that people talk about. There's augmented reality. You take out your phone and you can see Pokemon Go, right? This is Nintendo's thing, and their developer portal runs on Liferay. But besides augmented reality and virtual reality, we also have now what we call mixed reality. This is Ronnie Abovitz from Magic Leap holding a photonics chip. It is not a lens. That's what he says. So when you put on this photonics chip, you see this, right? And his words are, it processes a digital light field signal that mimics how the visual part of the world talks to the brain. In other words, it's trying to talk directly to the brain. They've raised $1.4 billion with no public product yet. So somebody really believes that this stuff can work. And it only touches the visual aspect of your brain. What would it take to touch all the senses? Maybe something like a holodeck, right? Maybe one day we'll have it, but it'll use a ton of energy in order to do this kind of stuff. So maybe there's a simpler way. Maybe one day we'll be just jacked in like this to cover all of our senses. Or maybe we already are, right? I actually think we live in a simulation. And let me explain. I'll start with Albert Einstein. So the prevailing theory of the 20th century was that the universe was static, but infinite in age and size. It just went on and on, okay? And in 1917, when Einstein penned his theory of general relativity, he realized that his math required an expanding universe to work. But everyone believed back then that the universe was static. It was not expanding. He couldn't see how good his math was. So in order to fit in with the worldview, he hacked his math. And he basically threw in this lambda constant that he called the cosmological constant. He's like, just throw this in to make it work. Shortly after, there's a guy named Edwin Hubble. Here is in LA looking at the Hooker telescope. It's a powerful 100-inch telescope, the most powerful of the day. And at the time, people believed that the Milky Way was all that there was to the universe. He's looking out, and you can't see my mouse, but if you look at the smallest square box, that's what you see where it says V1. And if you look at the bottom right-hand corner where it says Edwin Hubble noted VAR, so that's his handwritings on these metallic plates that recorded stuff. And he's like, look, this star is changing in its brightness over time. It was a pulsating star. It's called a Cepheid. And you can use it to measure distances. And what people called back then the Andromeda Nebula, he realized was actually a faraway galaxy. And in 1925, New York Times called them island universes. They didn't even have words to describe another galaxy, just like, it's just another universe out there. But once he saw these giant, massive structures, he saw something else. That for these galaxies, the farther they are from us, there's a redshift in the light spectrum of these galaxies. That the farther away they are, the faster they were shifting away from us. And the only thing that could explain this empirical evidence was that the universe was expanding everywhere. And Einstein saw this. And space itself was expanding. And this was mind-boggling. Scientists for years did not want to believe this, that the static universe was just the wrong way of seeing things. It fooled even Einstein when his own math showed him that it must be so. And why didn't they want to believe that? Because if everything was expanding, that means there was a point in time where there was a beginning. And that was absolutely ludicrous. The universe was supposed to be infinite in age and size. How could there be a beginning? But now it's accepted science. And we call it the Big Bang Theory. 14 million years ago, in a hot, dense cloud, blah, 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 it all started with a Big Bang. Hope you guys watch that show here. Okay, so, well, how did it start? It started from a singularity. I asked a scientist, what's a singularity? It means we have no idea what it is, it's just nothing, okay? So, and this is one of the prime reasons why I believe we live in a simulation. It's almost like you're a VM, and you look at the log files, and you see, oh, there's a finite number of logs. There aren't an infinite number of log files. There's a finite number. Oh, and as I look at the timestamp of each log file, oh, this is the first log file. What in the world? So right at that very beginning, and that infinitesimally small point, okay, there was all this energy, and space and time began. That's how I believe our simulation started. And at that point in time, all the energy and matter, right, and antimatter that exists in the universe, all just booted up, and it's all there. There's no more matter, as far as we can tell, that's being added to the system. It just was, and then from this tiny point, bam. So that's why I believe it, okay? Because we had a beginning. But it's not just matter and energy that started at that point. It's quite strange. So this is a cheat sheet from that I found on the internet for a physics test. So on there you see right up here in the middle constants and diagrams. So it's very strange. Right when that point started, the gravity constant, it's big G, the mass of an electron, laws that fit mathematics on the side, all those things are part of this simulation. E equals mc squared. Why does it have to be that way? All right? So if you don't think that's such a strange thought, let me introduce you to a guy named Richard Feynman. He would have gone to Columbia, except there was a quota for the number of Jews who could attend Columbia University. So instead, he went to MIT. After that, he got a PhD at Princeton, and when he applied to Princeton, he got a perfect score in his physics entrance exam. And by the time he graduated, he gave a seminar, and in his very first seminar, Albert Einstein shows up. He was 23, and this is what was written about him. At 23, there was no physicist on Earth who could match his exuberant command over the native materials of theoretical science. Feynman seemed to possess a frightening ease with the substance behind the equations, like Albert Einstein in the same age, like the Soviet physicist Lev Landau, but few others. He worked on the Manhattan Project, the atomic bomb. He claims to be the only guy to see the Trinity nuclear test explosion with his bare eyes. He later taught at Cornell and at Caltech. And this is what he wrote. The rules, the laws, okay, that describe nature seem to be mathematical. This is not a result of the fact that observation is a judge, and is not a characteristic necessity of science that it be mathematical. It doesn't have to be. It just turns out that you can state mathematical laws, in physics at least, which work to make powerful predictions. Why nature is mathematical is again a mystery. And we're seeing math everywhere, more and more. Let me show you. This right here is from a guy named John Wallace, Arithmetica Infinitorum, 1655. It defines pi as a product of an infinite string of ratios made up of integers. It's basically a formula This is pi. We always find it strange, so here's a formula for it. So last year, 2015, Carl Hagen, I think it's from University of Rochester, while teaching a class on quantum mechanics, he's talking about how to measure the energy states of a hydrogen atom. So he's going through the math of it, and he's teaching his students. And while he's doing that, he noticed a pattern. He's like, wow, I'm seeing a pattern in the energy states of hydrogen. So he brought along his colleague, Tamar Friedman, who's a mathematician and physicist, and she quickly realized this is the Wallace Formula. And this is what they said. Well, it's the first time that the Wallace Formula for pi had been derived from physics and quantum mechanics. And the math world and the physics world went crazy over this paper. And he wrote, what surprised me is that the formula occurred in such a natural way in the calculations, with no circles involved. It's not like they saw a circle and they measured pi. There's nothing to do with circles. But it helped them determine the energy states, said Hagen. This is what else he said. We weren't looking for the Wallace formula for pi. It just fell onto our laps. It was a complete surprise, Friedman added. I jumped up and down when we got the Wallace formula out of the equations for the hydrogen atom. Another mathematician, Moshe Makover from King's College London, said, it's a cunning piece of magic. Magic. Another mathematician from Forbes said, this almost seems like magic, that a formula for pi is hidden inside the quantum mechanics of hydrogen atom, right? That's a base element, is surprising. And just like Feynman said, it's mysterious. It indeed is surprising and mysterious, but maybe it shouldn't be. How do we build video games? With math, right? Maybe we do exist in a simulation. But it's not just video games. Think compilers and JVMs. And remember that cheat sheet that I just showed you a few seconds ago? Check out this cheat sheet. It's a Java quick reference guide. What do you see in there? A constant value for a byte, short, int, long. A program, these are immutable constants. You cannot change them. Any more than we can change the value of gravity, or any more than we can change E equals MC squared. And you see all these mathematical laws, right? If logic statements. So this is the second reason why I believe in a simulation. First, we had a beginning, and second, we're bound like programs that cannot break out of our compiler. We're bound by these constants and laws, no matter what you do. There's no amount of money, no courts that could ever change the value of the mass of an electron or the speed of light. It just is. These laws are there. We cannot change them. And that's why I believe we live in a compiler. And third, and that's most relevant for today, the universe is freakishly modular. Let me explain. That right there is a planetary model of an atom. About 5% of our universe is the matter in the universe is this kind of matter. The other 95% is dark matter and dark energy, which is 95% a lot greater. I'm not going to go into it because scientists don't have a clue what this dark stuff is, and they just call it dark. It's another word for invisible. They don't know what they're doing, so it's just out there. But 5% of it is what I will talk about. And of that 5%, everything we see, all this, atoms. Okay, and there's a finite number. They say there's about 10 to the 78th to 10 to the 82 atoms in the universe. It's about 100,000 quadrillion vigintillion atoms. This atom here happens to be carbon. You can tell it's got 6 electrons. So, interesting. How are all atoms different? They have a different number. This is a periodic table. So everything we see here breaks down to atoms, okay? You can break down atoms some more, but for now, we'll just say atoms are the basic building block. And there we are. You have, they have a different number of electrons, you have a different number of protons and neutrons, and there you have it. This is what they are. To me, it's almost like this is your java.lang and your java.util. This is what you get to work with. Why is gold the way it is? Well, it's got one more electron or one less electron than something else. Why does it have those properties? It just is. This is provided for you, right? You can't change it. Now, how do these elements come to be? This right here is called the Mystic Mountain, okay? This was taken by the Hubble telescope. And basically, they call this a star factory. So right after the Big Bang, you have a bunch of hydrogen and energy just expanding outward. And over time, these hydrogen gases just kind of float around, and they have properties. They have gravity. And based on the laws of physics that just exist in our simulation and are the way they are, and based on the gravitational constant that is what it is, that cannot be changed, these gases come closer together. And as they come closer together, again, based on the laws of physics, it gets hotter and hotter and hotter. And so you have the sun. That's where the sun comes from, right? It's just a bunch of this hydrogen. And as you have gravity bringing them closer together, you have a larger and larger mass structure, which then causes more and more hydrogen to come. And within that gravity, you have 4 hydrogen atoms that fuse together, 4 atoms that then become one helium atom. And from that, you have a loss of mass, which then has a bunch of energy, equals mc squared. Bam! And that energy has to go somewhere. That's called nucleosynthesis, where you have these things that go from 4 atoms to 1, and then and that's how we make helium. Now, over time, okay, as the sun uses up all of its hydrogen, because you have a limited finite number of hydrogen, and all those turn into helium, and over time it just ends up burning up, runs out of fuel, and then eventually it's supernovas. This right here is a photo of the Crab Nebula. Right? And when it's supernovas, now you have a bunch of helium floating around. Well, what do you do next? The helium starts floating around, and based on the laws of gravity, they come back together. Okay? And they form a different type of star. And this is how all the elements get created. Right? It takes a ton of gravity, a ton of energy. And for example, these 2 neutron stars, okay, they'll rotate around each other, and then they'll just, bam, run and collide. And then it'll explode. It'll have this big, huge gamma explosion, and all of the energy in it is released all at once. And when that happens, it spits out, because of all the nuclear fusion that happens, it spits out gold nuggets the size of planets. And that's where gold comes from. So that's why I can't just take lead and turn it into gold. I could, if I could modify the properties in it of the atom, but it just takes a whole lot of energy, and we're not going to do that here. And all of our building blocks come this way, and all of our building blocks are so similar, just tiny changes in properties. And back to our solar system, right? Where the sun has not gone supernova yet. That's a nice thing. So right here is a sun in the middle, and then you can see red letters, Earth. Remember planetary model of an atom? Well, why do you think they call it planetary? Because they looked at an atom, and it looked freakishly like the solar system. Okay? Same pattern. And we have a bunch of these elements because they all came from the stars. Now let's see how well this scales, how this modular structure scales, right? You have the Earth and our solar system. And here, we have our solar system across a bunch of other solar systems in our interstellar neighborhood. And then here, we have our interstellar neighborhood in the midst of the Milky Way galaxy. And here we have our Milky Way galaxy in our local galactic group. Feeling small, guys? I'm feeling very small. And then here's our local galactic group of galaxies in our Virgo supercluster. See that one dot, that red dot? That's that other cluster. Now it's the Virgo supercluster. And now this is a Virgo supercluster, one dot, amongst our local superclusters. And then that local supercluster, one dot, the observable universe. That's freakishly modular, guys. Up until a week or two ago, scientists believe that there are about 200 billion galaxies in the universe. Now, with the latest New York Times article that quoted a published paper, we believe there are about 2 trillion galaxies, at least. And yet, it's a fishbowl. There's a limit to this JVM that we live in. It may have 40 gigs of RAM, but it's limited, right? And each galaxy has about 100 to 400 billion stars. And these galaxies and these local structures, when they come together, they become different structures. They call them the Boss Great Wall, the Sloan Great Wall, the Hercules Corona Borealis Great Wall. And these are great walls, structures of galaxies, billions of light years across. The universe is freakishly modular from the perspective of stars. What about biology? 1665, Robert Hooke coined the word cells. He examined a cork from an oak tree with a 30x microscope. And within it, he did not see this. But now we have knowledge of what a cell looks like. Just as our better telescopes showed us just how massive the universe is, better microscopes show us the life of a cell. And each of these are intricate machines, and Peter will go into some more, so I won't. But I care a lot about this because that right there, bottom left-hand corner, that's a lysosome. And my daughter has a mutation right there from a protein, a machine in there. But I'll get into that another time. So right here in the nucleus, you have DNA. And there's a whole world living in here. And what's DNA, okay? So it's just basically like this long double helix. It's source code, okay? And it's made up of, just basic elements of what? Adenine, cytosine, guanine, and thymine, which is these are molecules, I guess, made up of nitrogen, hydrogen, oxygen. But think about it. Wow, in biology, those same basic elements, you combine them, they become a molecule. You combine them, they become the basic building blocks of DNA, right? And if you look at human DNA, it's made up of about 3 billion base pairs, or about 770 megabytes when you represent it in characters like this. But now remember, even A itself is complicated. It's a bunch of those other chains. And there's about 37 trillion cells in your body. So imagine 37 trillion cells, 770 megabytes. Bam, a ton of information just got passed, far more than what our internet can handle. And then let's look at how this stuff builds up. So you have your cell, which Peter will go into and dig in more about the intricacies of a cell. But you have a cell, which is made up of atoms, which you have different compartments inside, different machines. And that group together becomes tissue. A bunch of tissue grouped together becomes an organ. A bunch of organs grouped together become an organ system. And a bunch of organ systems put together become an organism. This is freakishly modular. Why don't we have cells the size of large elephants? Because it doesn't work that way. You take a bunch of small cells, group together, they do something, and group together, do something else, and then you get an elephant. The universe just is not made this way. You don't see a star the size of the Milky Way galaxy. No, there's a limit based on the laws of physics and everything of how big and how small a star can be. Right? So my two reasons were interstellar, just look at the stars, and then look at biology. And then now, let's also look at sociology. One human unit, an atom, a molecule, in a family, in a neighborhood. And each of these atoms have different properties, right? Some grow up to be doctors, some grow up to be computer programmers, right? And they also band together based on things they like UCLA football. And it is freakishly scalable even in sociology. As we identify in our nations, there's about 7.4 billion of us. So to quickly summarize my argument, there's a lot of smart people who believe we live in a simulation. I believe in one because the universe had a beginning. The elements are limited. And then there's the laws and constants, which are immutable. And then the universe is freakishly modular. And how is it modular? In 3 ways. From the stars, in biology, and in the way we interact with each other. How does that apply to us? A few weeks ago, I got an email from O'Reilly. It said, the 5 reasons to finally learn design patterns. Okay? I was like, oh, interesting. I love design patterns. The 5th reason was to find truth and beauty. Why would an O'Reilly article tell me to find truth and beauty? It must mean, as programmers, we often see falsehood and ugliness. I was talking to Wolfgang last night while I was eating dinner, and he was telling me how in 6.2 he had to do this hack in order to get something done. And he told me afterwards, it was a hyperbole, he had to shower for 2 hours because it was so dirty. And I told him, that same component you're talking about, it's modularized in 7.0. And he's like, yeah, it wouldn't be ugly if I had to do it this way. Wow, intrinsically, what is up with this truth and beauty that we long for? Because we see falsehood and ugliness. Remember Einstein, back to his lambda constant. He wrote this in 1947, okay? After he flew out to LA to meet Edwin Hubble and looked at his data, and he just felt really bad. Because he could have predicted it through math. And if you can predict something through math that correlates in the real world, that's like the ultimate triumph, But Einstein has other triumphs, so he's okay. So he wrote to Liferay, I think he's a French guy, in 1947, the introduction of such a constant, his hack constant, implies a considerable renunciation of the logical simplicity of the theory. Since I introduced this term, I had always a bad conscience. I am unable to believe that such an ugly thing should be realized in nature. Why, Einstein? Why is it that you couldn't have an ugly formula in nature? Why? Why must it even be bound by mathematics? I believe it's because we live in a simulation. And if we live in a simulation, and this universe that we live in is orderly, beautiful, and modular across all fields, stars, biology, human interactions, then it must apply to how we as computer programmers write source code. If you write code that's not modular, just like a cell cannot be the size of an elephant, it will not scale. You're trying to do something that's impossible. And that's what we realized at Liferay. We're like, oops, we ran into the bounds. I can't get a faster computer, that's not gonna fix it. Because of human interaction, how everything goes, we must modularize our code. Or we just will hit a wall, like the speed of light. We're not gonna get past it. I didn't get into the details of exactly how to write modular code, but there's a ton of people here who will, and they'll do a better job of it than I can. I'm simply a Padawan with a pretty good midichlorian count, but I'm still just a Padawan. There's a Yoda who's going to be speaking next. You can see the white hairs and the similarity. His name is Peter Kreens. He is the OSGI Yoda. You can look him up on Wikipedia. He's done 40 plus years of it. I had the pleasure of eating with him a few years ago at the Liferay HQ in LA. And he was sharing with me earlier how even 40 years ago, when he didn't have the names for modularity, he was already doing it. It was just intrinsic in his nature. He just knew this is how you do it. That's a guy to learn from. So I'd like to prepare for him and welcome him up.